Hello, guys. Good morning. Good morning, everyone.
Good morning, sir.
Good morning, sir.
How are you doing?
Fine by grace, sir. I hope you are good.
I'm also good by God's grace. All right. So kindly inform your colleagues to join. I'm waiting for a minimum of 20 students so we can start. Currently, we are 14. We need 6 more students to start, please. All right. Good morning. Once again. Thank you for joining this class. I think we should start now. Last week, did we cover this storage structure? Did we talk about the SSD, the storage device hierarchy?
Yes, please.
Okay. Did we talk about the single processor and multiprocessor systems? The asymmetric and the symmetric?
Yes, please.
Did we talk about the multi-programming and multitasking?
No, sir.
All right, thank you. Okay, so I gave you an assignment to go and look out for how many processors your computer has, how many CPUs or how many cores there are in your CPU. Did you check it? Did anyone check how many cores there are on their CPU? So nobody checked. Benjamin Adam, Boating Gertrude. Did you check how many cores there are on your CPU? Afuakwa Philip, did you check how many cores there are on your CPU? David Adom, are you guys with me?
Yes, sir.
So I'm asking you, did you check how many cores you have on your CPU?
Yes, sir.
Okay, so how many did you find?
Sir, mine has 2 cores and 4 threads.
2 cores and 4 threads. Okay.
Yes, sir.
All right, thank you. Is there anyone else who checked? All right, Jay, thank you. Jay Janet. Jay Janet, how come your voice is masculine?
Sir, please, it's me. Wait for the what?
Oh, okay, Clifford, you spoke. Okay. All right,
Yes,
Clifford.
sir.
Sure, good. Good. Nobody else checked. Clifford, please give me your index number.
Okay, sir. My index number is 040
040,
919
919, okay.
082.
082. Okay, good.
Yes, sir.
All right, thank you. Okay, 082. Good. All right, guys. So let's start with today's class. Let's continue from the operating system structures. If there are no questions, are there any questions from what we did last week? Are there any questions? Yeah, Apreku, you've raised your hand.
Sir, please, you said you were going to upload the video for us. It wasn't uploaded.
It's there.
So I checked this done. It wasn't.
It's there. This morning, I also verified this morning, and it's there.
Okay, so I would have to check again.
Please do. All right. Thank you. Okay, so let's look at the operating system structure. So you know that one of the most important aspects of the operating system is its ability to multi-program. When we say multi-program, we are talking about the operating system's ability to execute more than one program at a time, right? Are you with me?
Yes, sir.
Yes, sir.
So when we say multi-program, we are talking about the operating system's ability to perform or execute more than one process or program at a time. So if you look at the CPU, the expensive CPUs that we have in our system, excuse me, please, someone is calling. I don't know whether it's a student or not. Kindly hold on. Yes, hello. Good morning. Okay. Yes, Osebonsu. The class is ongoing. Which is it level 300? Which of the groups? Are you in group A or group B? Is this a satellite campus? Which campus, please? Kumasi campus. You are the class rep. Okay, the class is ongoing. It is online as we speak. Do you have a group? Okay, kindly send me hi on WhatsApp so that I'll send you the link. We just started the class, so you guys can join. Send me hi so that, yes, no. Okay, no. Do you have my Vodafone? No, this number is not on WhatsApp. Okay, I'm going to send you a hi on WhatsApp. Please hold. Okay. Okay, my WhatsApp number 020 458 4448. Yes, sure. Okay. Hello guys. I'm sorry, but we have the satellite members from satellite campus. They have to join this class. Last week they couldn't join. So let's just wait some few moments for them to join. Okay.
Okay, sir.
All right. Thank you so much.
Sir, please, while you wait, sir, please, the video I was talking about was last week's class. It wasn't on the CPU, it's not loaded.
Come again.
Last week's class video, the one they're recording it, they said we were going to upload it. It wasn't there.
Really?
Yes, sir.
It's there. I'm coming.
Sir, it's not.
Wait, I'm coming, please. I hope you can see what I just typed. We are waiting for colleagues from satellite campuses to join.
Yes, sir.
Is it visible?
Yes, sir, it is.
Okay, good. So please, yes, a few moments, let's say 5 minutes, for them to join us. Let me send the link to him. Good. Okay, so what were you saying? Come again. You said a video, or is it you mean the recording?
Yes, sir.
Okay. I did not send the record. Yes, I haven't sent the recording. Because I was hoping to complete this this morning's class because it is one chapter. Chapter 1. I wanted to finish with the chapter so that I'll put the two together, and then we have one video for chapter 1. Then I'll send it to you. Right? Otherwise, if you don't like it that way, I can just upload the first one and then later upload this one also. So how do you want it to be? Or should I send it to the class rep?
Sir, please can send it like that.
I should send it like that.
Yeah.
Okay, fine. All right, good. Then I'll send it to I'll send it to the class rep. Or do you want me to put it on the Moodle platform?
Yes, please, on the
The
model
GC.
platform.
Please on the Moodle platform.
All right.
So let's do together.
Okay, fine. Then I will upload it on the Moodle platform. But remember that all these lecture notes are available on the Moodle platform for all the chapters that we are going to look at from chapter 1 to the end. They are all available on the Moodle platform. And when you go there, you should be able to see them. So please always go there and download them for your use, right? And there are other articles that are available. Okay. So do we have members from the satellite campus now? Do we have members
Yes,
from
sir. Yes, sir.
Okay. Okay, good. iPhone, could you please rename your account so that we will see your name?
Okay, sir.
Sure. Thank you so much. Have you shared the link with your colleagues?
Yes, please.
Okay, so they are all with us.
Yes, sir.
Okay, are you sure? So can we start? I mean, can we start with the class?
Yes.
Yes,
Right.
sir.
Okay, good. Great. Okay, guys, let's go back and start with operating system structure. So, like we were saying, one of the most important aspects of the operating system is for the operating system to be able to do multi-programming. And when we say multi-program, we are talking about the ability or the capability of the operating system to run more than one program. Okay. Remember, we have expensive and sophisticated CPU, computer hardware, all the components on the computer are so expensive. And so we can't afford to have the computer running just one program at every single time. Okay. Imagine if you want to do your Facebook, okay, and you are playing music, you have to finish with the music before you can do Facebook. You can't be doing Facebook and at the same time be doing WhatsApp on your phone. Every time you want to do a new program, you have to close the existing one. I'm not sure anyone will be happy with such a system. So multi-programming increases the CPU utilization by organizing jobs, okay, so that the CPU will always have one to execute, so that at every point in time, the CPU will not be idle. The operating system keeps several jobs in memory simultaneously or simultaneously, depending on the school you attended. So it is the work of the operating system to schedule the jobs in the system so that at any point in time, the central processing unit or the CPU will have some job to execute. Now, we also know that the main memory is usually too small to accommodate a lot of jobs, okay? So in the hard disk, we have what we call the job pool. We have what we call the job pool. And this job pool contains all the jobs that are to be executed. This is on the hard disk, okay? So when the operating system realizes that there is enough space in the main memory, then it will pick the job from this job pool into the main memory, okay? Into the main memory. All right. This is the job pool. Okay, this is the job pool. The operating system picks and begins to execute one of the jobs in memory. Okay, when the job has to wait for some task. You know, last week we mentioned that when you are executing or when a process is being executed, it will be just a matter of time before the job asks for an IO or performs an interrupt. So when the job performs an IO in a non-multi-program system, the CPU ultimately will sit idle. But when you have a multi-program system, the operating system will simply switch the job that is waiting for the IO with a job that is waiting in the main memory. So let me give you an example here. Okay, assuming you have a job that is executing, let's say Facebook, okay, whilst the central process or the CPU is executing your Facebook, you start typing. Or better still, let's assume you have a calculator application. You know, when you put your calculator application on your computer, when you run it, you start typing your figures. Let's say you want to do 2 plus 2, okay, is equal to 4. Now what happens? When the CPU loads this calculator, what will be happening in the initial stage is what we call IO, input output. You are just going to start by typing your numbers. 2. When you press 2, it is an input. Then you press plus, it is also an input. Then you press 2, it is also an input. Then you press the equal to, that is also an input. Now, all this while, the CPU has not been called to do anything because this input is being handled by the special purpose microprocessor. Remember that in addition to the CPU, there are special purpose processors. An example is the input microprocessor. So when there is an input, the CPU relegates that task to that special purpose. So whilst you are typing 2 plus 2, the CPU is ultimately doing nothing. The only time the CPU comes in is when you press the equal to sign. Then the CPU will quickly perform this computation. It will add 2 to 2, and the CPU will give you an output. This is also an output. So once the CPU finishes with the computation, it will relegate that to the output processor also. Okay, so you see, in all these 5 operations, 1, 2, 3, 4, 5, in all these 5 operations, the CPU came in just once. So imagine all through these operations, the CPU was sitting doing nothing. It means that the computer or the operating system is not making good use of the CPU. Okay, so that is not acceptable. So what happens is that whilst the operating system, or whilst the CPU is waiting, while the current job is waiting for some IO, in a multi-programmed system, the operating system will simply switch to and execute another job. So whilst you are doing your typing on the calculator, the CPU can switch over to your Facebook application, okay? And then execute your Facebook, or it can switch to your WhatsApp application, okay? This is what we call the multi-programming, okay? Now, in a multi-programmed system, the system resources are utilized effectively, but they do not provide for user interaction. So here we are concentrating on multi-program. That is the ability for the CPU or the operating system to switch programs, to switch between programs. In this type of system, there is no user interaction. What happens? We have what we call the time sharing or multitasking. The multitasking is a logical extension of the multi-programming. So in time sharing, the CPU executes the multiple jobs by switching among them. But the switch occurs so frequently that users can always interact with the program. So this is a multitasking timeline or a time sharing timeline. The time for the CPU is divided into time slots. Okay, so as you can see on the screen, the CPU time has been divided into time slots. Slot 0, slot 1, slot 2, up to slot N. So at every time slot, the CPU switches among the various programs. So if at time 0, the CPU is working on Facebook, time 1, it will be working on Instagram. Time 2, it will be working on VLC, in that order. Okay, so when this happens, the CPU allows for interaction with the user. Here, the CPU can delegate the time slot 3 for user interaction. Okay, now this time sharing requires an interactive or hands-on computer system. Okay, now let's see. In the time sharing, the user will give an instruction to the operating system, okay, using an input device, for example, keyboard or maybe a mouse. And then the user will be waiting for an immediate response, like we talked about the calculator. Okay. Now, in this time sharing, the response time should be so short. It should be short, maybe less than a second, like when you press the enter on your calculator. You notice that the response is very short. Okay. The time shared operating system will always allow many users to share the computer simultaneously. Okay. As the system switches rapidly from one user to the next user, each user is given the impression that they are the only ones using the CPU. It's like you're playing music, you are doing Facebook, you are sending email. All these are working simultaneously. And sometimes you even forget to think that the CPU is being shared by all these applications. That is time sharing for you. Okay. Any questions, please? All right. So in the computer system, if a program is in the main memory and is being executed, we call that a process. So a program that is being executed is called a process. A process typically executes for only a short time before it either finishes or it needs to perform an I/O. So like I was telling you, if you take your calculator, the most part of the operation in the calculator is usually an I/O, input output. The CPU comes in only for a short period of time. Okay. Now, rather than thank you. Rather than letting the CPU sit idle whilst the other computations, are taking place, the operating system will rapidly switch the CPU to the other program for other users. So even if you have multiple users using the same computer, the CPU will share, the operating system will share the CPU time over the various users. So at time A, the computer or the CPU will be working on user A. At time B, the CPU will be working on user B in that order. Okay, that is also under the time sharing. All right, let's look at the job scheduling and how the memory is managed. So time sharing and multi-programming require that several jobs are kept in the main memory. If there is not enough room in the main memory, then the system must choose among them. You know that most of the time, the main memory is limited when it comes to space. And because of that, we can't put all the programs or the jobs in the main memory. Okay, that way, we have to find a way to choose among the programs that we want to bring into the main memory. So making this decision is called job scheduling. Of the many jobs that must come into the main memory, we have to decide which one to bring into the main memory, okay? And this is done using what we call the job scheduling protocols. We'll look at a few of them later in this class. For example, we have the shortest job next, where the job that has shorter time to execute will be given the priority. We also have the first come, first serve, where the first job that entered the main memory will be executed. Okay, we have the last in, first out. All these are different scheduling algorithms that are used in the selection of the next job into the main memory. Also, having several programs in the main memory at the same time requires some form of memory management. We said that the main memory is a smaller memory space, and therefore, if there are supposed to be several programs in the main memory, then we need to manage that memory in an efficient way. So we will look at memory management also later in this class. Then, if several jobs are ready to run at the same time, the system must choose among them. Okay, making this decision is also called the CPU scheduling. Okay, if you have several jobs in the main memory, how does the CPU choose among them? Do we have some jobs that are having higher priorities? If it is a multi-user system, do we have users who have higher priorities than others? All these are taken into consideration before the CPU chooses which job is executed. And that will also be looked at later in this course. Right? Good. Now, in a time-sharing system, the operating system must ensure reasonable response time. When you give a job to the CPU, or when a user requests the operating system to perform a task, the operating system has to make sure that it does not take too much time for the user to get response. This is accomplished through swapping, where processes are swapped in and out of the main memory to the disk. Okay, assuming you are printing a document, and then you decide to open your Word document on the computer system. Whilst you are printing, you want to open another document. At this time, are you expecting the operating system to complete with all the printing before your document is opened? Assuming you are playing music and you want to open a file, are you expecting the operating system to finish playing all the music before your file is open? That is not acceptable. That will increase the response time of the computer system. Therefore, the operating system does what is called the swapping. When there is a job in the main memory that is taking too much time, or that is not using the CPU, the operating system will swap that job with a new task that requires urgent attention. Swapping is achieved through the use of virtual memory. Okay, we'll look at virtual memory pretty soon. This is a logical memory, usually not part of the physical memory, assuming you have 2 GB as your main memory. The computer automatically creates another space called the virtual memory. And this virtual memory is used in conjunction with the main memory in order to swap your processes in and out of the memory. This technique, this virtual memory technique, allows the execution of a process that is not completely in main memory to be switched or swapped in. We will also talk about virtual memory later in this course. The main advantage of the virtual memory scheme is that it enables the user to run a program that is larger than the actual physical memory. Imagine you have just 1 GB. Some of us on our phones, the main memory is just 1 GB. And you want to run tempo, you want to do tempo run game on your phone. You want to do highway surface, those games that we play on our phone. Yes, subway surface. Okay, thank you. These games, some of them are more than 1 GB. Does it mean that your game cannot be run? It should not happen so. Therefore, the phone or the computer creates a virtual memory where sections of the game can be copied. Remember, your 1 GB main memory is already harboring the operating system. If you're using Android, your Android is on the main memory. So if 1 GB, assuming the Android takes 200 megabytes, you have just about 824 megabytes of memory. That is too small to run the tempo run or the subway surface. Okay, so the virtual memory allows you to run some of these programs that are larger than the memory capacity of your main memory. So we'll talk more about the virtual memory later in this course. Now let's look at the operations of the operating system. Now, there are two modes in every operating system. Now, if we remember in our previous class, we mentioned that the operating system is interrupt driven. That means the operating system will continue to run until it has been interrupted. When the operating system is interrupted, then it will retain control to the process that has interrupted it. Now, in order to ensure the proper execution of the operating system, we should be able to distinguish between when the operating system is executing and when a user code is executing. Okay, so we have the operating system code and the user-defined code. We must know at what point is the operating system code running and when the user-defined code is running. The computer system must be able to differentiate among these various modes. So there are two modes in the operating system. We have the user mode and the kernel mode. I'm sure you know and remember the kernel. The kernel is the core of the operating system. From our last week class, we mentioned that the kernel is the core part of the operating system. So that is one mode. We have the user mode and the kernel mode. This kernel mode is also called the supervisor mode or the system mode or the privileged mode. Okay. Now, how does the operating system differentiate? So there is a hardware bit. There's a hardware bit called the mode bit. This mode bit is used to indicate whether the operating system is in the kernel mode or in the user mode. So the value for the kernel mode is 0. So if the operating system is executing in the kernel mode, then the hardware bit or the mode bit will be 0. If it is executing in the user mode, the mode bit will be 1. Okay. Now this mode, this dual mode, allows the operating system to protect itself and other system components. Are you with me?
Yes, sir.
Okay, good. Let's continue. So let's see what happens from the time you turn on your computer. When you turn on your computer, that is during system boot, the hardware starts in the kernel mode. Okay, so remember last week, we talked about the bootstrap. The bootstrap is the firmware that was loaded by the manufacturer of the computer system. Okay, so during the bootstrap, the hardware starts in the kernel mode. Okay, then the operating system is loaded and it starts the user applications in the user mode. So till the time your operating system loads, the computer is running in the kernel mode, which is value 0. Okay. When an interrupt, please hold on, my HOD is calling me. Hello, senior. Hello, senior. Yes, sir. Good morning, sir. Yes, please, I'm having class. No, that was yesterday's class on Wednesday. But yesterday, one of the students told me that you have swapped the class with me, and so instead of Wednesday, it has been taken to Friday. This is that one was. I have to check on mine. Please hold on. That one was BIT level 300, satellite campuses. But this yesterday when I called the student, he told me that the class has been switched to Monday with you. Wow, this morning I also have class with a class student at main campus. So this class, as I'm having right now, is a combination of the main campus and then the satellite campus. Then this is introduction to operating systems. And the one on Wednesday is also introduction to operating systems. So I think perhaps there was that confusion. The Wednesday is a satellite campus, BIT top up level 300 for all the satellite campuses. Then this one here is level 300 section A main campus. And then satellite campus is BIT level 300 regular. So yesterday's was satellite campus top up. And this morning is satellite campus level 300 regular. Okay, so you maybe after the class, we will talk and see how we can. Yes, sir. All right, sir. Thank you. Guys, I am sorry about that. That was my head of department here in Kumasi. Okay, so after the bootstrap, the operating system loads and then it switches from the kernel mode to the user mode. So the user mode is where user applications are executed. So your Facebook, your Microsoft Word, your Microsoft PowerPoint, whatever you have on your phone or your computer is executed in the user mode. So whilst your application is being executed, whenever there is a trap or an interrupt, assuming your Facebook wants to save a file on the hard disk, that is an interrupt. Assuming your Facebook requires entry, you are typing message to be posted on Facebook. Assuming you are on WhatsApp and you have to type a document or you have to take a photo, you switch from the WhatsApp to your camera app. All these are examples of interrupt. And the trap is where there is an error. Assuming there is an error or there is an invalid calculation or something in your application, that is a trap. So when a trap or an interrupt occurs, then the hardware bit, that is the mode bit, switches the operating system from the user mode to the kernel mode. Okay. So usually you remember sometimes the computer will ask you, are you sure you want to perform this? And then you say yes. Immediately you say yes, then operating system is sure that you know what you want to do. So it switches from the user mode to the kernel mode. Thus, whenever the operating system gains control of the of the computer, it is in the kernel mode. So when you want to save a file, the operating system will now go into the file system and create your file for you. When you want to edit a file, the operating system will go into the file system and edit the file. You want to delete a file, the operating system will have to go into the file system. Therefore, it will ask you, are you sure you really want to delete this file? At that time, it will switch from the user mode to the kernel mode. The system always switches to the user mode before passing control to a user program. So after the operating system has executed in the kernel mode, it switches back to the user mode before you continue to use your Facebook, your WhatsApp, or your Word document. Are you with me on that?
Yes, sir.
Any questions, please? Right. Good. If there are no questions, let's continue. Lakaka, you've raised your hand.
Yes, sir, please. How would the processor determine that the job is lower priority or higher priority?
How does the what? Come again.
The processor determines whether the job is higher priority or lower priority.
So okay, thank you. It is the operating system that tells the processor. By processor, I hope you mean the CPU. It is the operating system that tells the CPU whether a process is a high priority or a lower priority. We will look at scheduling and we will see how a job is identified as a high priority job or a lower priority job.
Okay, sir.
Thank you. Mr. Ahmed, your hand is up. Rafatu. Ahmed.
Sir, good morning.
Good morning, madam.
Okay, sir, please, I wanted you to go over the user mode and kernel mode. I'm a little bit confused.
All right, the user mode and kernel mode. I'll do that.
Yes. All right, thank you.
So what we are saying is that there are two modes in the operation of your computer system. We have the user mode and the kernel mode. Your computer can operate in the user mode when it is working on user applications like Facebook, like VLC. When it is executing instructions that do not modify the computer configuration, the computer or the operating system executes in the user mode. Okay, but whenever there has to be a change in the computer system, the operating system has to switch from the user mode to the kernel mode. Now, if you remember in our last class, we said that the core of the operating system is called the kernel. The core of the operating system is called the kernel. Now, let me give you examples of some of these applications that require the kernel mode. You know, when you execute your CMD, the command prompt, immediately you enter your command prompt, the system asks you if you really want to execute your command prompt. Why? Because every command that is executed in that prompt is an elevated command. It is a privileged command that can modify your computer in a significant manner. Therefore, the operating system wants to make sure if you know what you are doing. That is why it usually asks you questions. Are you sure you want to switch or you want to open the command prompt? And you say yes. Okay. Then we have applications that are light, that do not make any modification to the core of the operating system. Those are in the kernel mode. Now, on the computer hardware, there is a bit called the mode bit. This mode bit is, guys, please hold. Please. Hello, senior. Yes, sir. Okay. Okay. All right, sir. Okay, sir. Okay, sir. Thank you. Okay. Sorry, guys. So members from Satellite Campus, some of you were with Mr. Nuku. Have you now joined us?
No, they are about to.
They are about to.
Yes, please.
We've joined. Some are still joining.
Okay, some are here. So do I have students from Kumasi Satellite Campus? Kumasi
Yes,
Satellite
sir.
Campus.
Yes, sir.
And what about Takrady?
Yes, sir.
Yes, sir.
Okay, Ho,
Yes, sir.
Koforidia.
Yes, sir. Yeah, you.
Okay, very good. So this is a combination of all the campuses at GCTU. All right, so guys, welcome to this class. So after this class, I will discuss with Mr. Nuku and we will find a better solution to this clash. Okay. All right, thank you all. So we are looking at two modes of operation in the operating system. We are saying that the operating system can operate either in the kernel mode or in the user mode. Okay, and we said that there is a hardware on the computer system that is called the mode bits. These mode bits have two values, 0 and 1. When the operating system is executing in the kernel mode, the value of the mode bit is 0. When the operating system is executing in the user mode, the value of the mode bit is 1. Now, it is this dual mode operation system that allows the operating system to protect itself. It is the one that allows the operating system not to execute a privileged command in the user mode. Assuming the operating system allows a user to execute a privileged command, they could fidget with the configuration of the computer system. Let's say a user A wants to access the files of user B. This operation is not allowed because the operating system at that time will be executing in the user mode. Immediately you switch over to the kernel mode, you can now access the content of another user. So these are some of the reasons the operating system always executes in the user mode, and it switches to the kernel mode only when you are sure, by asking you questions and having you answer them. Okay. Please, Ahmed, is that okay now?
Yes, please, sir. Thank you.
Sure. You're welcome. Okay. So for the sake of those who just joined, let me continue from here. So what we are saying is that when you boot your computer, the hardware, that is the mode bit, starts in the kernel mode, which is 0. The operating system is then loaded. When you boot your system, there is what we call the bootstrap, the initial application that runs when you turn on your computer. It is called the bootstrap. At this point, the hardware or the computer is executing in the kernel mode. So in the kernel mode, your operating system loads. Immediately your operating system is loaded, then the kernel mode is switched to the user mode. This is where user applications run. So when you run your Word document, you double click on the file to run. It is running in the user mode. When you turn on your Facebook or your WhatsApp on your Android operating system, the operating system is running in the user mode. Then, Lumumba, you've raised your hand.
Yes, sir.
Okay.
All right. I have a question.
Please go ahead.
So you are saying that when the machine is booting, it's in a kernel mode.
Yes.
And then for it to move to the user mode, it asks questions.
No. No.
For it to move to the kernel mode, rather, it asks for questions for it to move to the kernel mode. Yes. So my question is, after the machine is done booting, where it asks you to, is booting, it's in a kernel mode. And when it asks you for your password, is it still in a kernel mode or in a user mode?
Okay. So, from last week, we talked about the first process in the operating system called the init. If you remember, when you turn on your computer boots in the bootstrap. Then the bootstrap will go and locate the operating system on the hard disk. It will load the operating system and it will bring it to the main memory. When it brings it to the main memory, the first process in the operating system is executed. That process is called the init. Okay, so when the init finishes loading, you get the login where you enter your username and password. So until the computer gets to the init, until the init is executed, the computer runs in the kernel mode. Immediately the init finishes, you get your login screen. At that time, the operating system has switched from the kernel mode to the user mode. So your login screen is in the user mode. Is that okay?
Oh, okay, sir. Okay, sir.
All right, good.
Thank you so much.
Sure. So while your operating system is in the user mode, so let's take the login that you just talked about. So when it gets to this point, your login appears. It is still in the user mode. At that time, you enter your username and password, then you press enter. When you press enter, the signal is sent to the operating system as an interrupt. Okay, you interrupt the operating system at that time. Now the operating system has to take your username and password to verify whether it is a correct user on the system and whether it is the password for that user. So that check is done in the kernel mode. So immediately that interrupt is generated, the computer or the hardware, that is the mode bit, switches from the user mode to the kernel mode. Then in the kernel mode, the operating system will verify the username and password. If the username and password is correct, then the operating system will log you in. You now come to the home screen, and then the operating system switches back to the user mode. Okay, so whenever there is an interrupt, the operating system switches from the kernel from the user mode to the kernel mode, because it is the kernel mode that will execute your instruction. Okay, so whenever the operating system gains control of the computer, it is in the kernel mode. I hope this will further explain or answer your question.
Yes, sir. Yes, sir.
Good. So the system always switches to the user mode before passing control to the user program. Every time you are interacting with the computer, it is in the user mode. When the operating system has to do something behind the scene, the computer or the system is switched to the kernel mode. All right. So the dual mode of operation provides us with the means for protecting the operating system from malicious users. Okay. Some machine instructions that have the potential to cause harm are run as privileged instructions. So a lot of these viruses, when they get into our system, they usually execute in the kernel mode, and that is why they are able to cause damages to our computers. Privileged instructions are executed only in the kernel mode. If an attempt is made to execute a privileged instruction whilst you are in the user mode, the hardware does not execute the instruction, but it will treat it as illegal and traps it. So remember last time we talked about trap. It will trap it to the operating system. So a lot of these antivirus software, what do? They monitor the mode of the operating system and find out if a request from the user is either causing the operating system to switch from the user mode to the kernel mode. If that happens, then the antivirus will assume that the action is coming from a malicious software or a virus. Okay, so some of the example for the privileged instructions include the instruction to switch to kernel mode. This instruction itself is considered a privileged instruction. an I/O control or an I/O operation. That is an input-output operation to create a file, to delete a file, to print a file, display something on the screen. All these are privileged instructions. Timer management. Lakaka, kindly mute your mic for us. All right, thank you. Timer management is also a privileged instruction where you want to change the date of your computer. All these, and then also the timer that we talked about when we say that the execution of the computer system is divided into time. We will go into detail when we get to time management. And then also the management of interrupt. All these are examples of privileged instructions. And in the execution of all these, the operating system has to switch from the user mode to the kernel mode. All right. We also have system calls. Okay. Now, last time we said that the operating system is interrupt driven. Interrupt means the computer or a process calling on the operating system to perform a task on its behalf. This interrupt is done through system calls. Okay. If you are in a user program, or if a user program is executing and it requires the operating system to perform something on its behalf, it performs what we call the system call. So the system call provides the means for a user program to ask the operating system to perform a task that is reserved only for the operating system. Okay, it is the method that is used by a process to request action reserved for the operating system. This usually takes the form of a trap to a specific location in the interrupt vector. Remember last week, we talked about the interrupt vector. This is a location where the interrupt code is stored. Okay, so system calls are nothing but interrupts that are emanated from user programs. Okay, now let's look at timer. Now, whilst a user program is being executed, it can fail or it can get caught in an infinite loop. Okay, when a process fails, it is a problem. When a process ends up in an infinite loop, it is also a problem. To prevent this problem from happening, we use a timer. Okay, a timer is set to interrupt the computer after a specific period. Okay, before turning over control to the user, the operating system ensures that the timer is set to interrupt. So we are giving you the CPU to execute. Okay, then we set a timer. A timer is set maybe every 2 seconds or every 1 second, every 500 microseconds. If the timer interrupts, then control is transferred automatically to the operating system. Okay. By that time, if the process has not finished its execution, the operating system might give the process more time. Otherwise, it will consider the process as a failed one. There is an error. Okay, so we give 2 seconds. So at every 2 seconds, there will be an interrupt. Then the operating system will verify if the process has completed its execution. If it has not finished its execution, then we'll give it more time, so another 2 seconds. After another 2 seconds, the operating system will verify if the process has completed. If it has completed, then control is returned back to the operating system. If it has not completed and it needs more time, we will give it more time. If it gets to that 2-second time and the operating system comes to verify and there is an error, maybe the process is no longer running, then it is identified or it is determined that an error has occurred. Therefore, whatever resource that was assigned to that process is taken back and the operating system will do the damage control. So a simple technique is to initialize a counter with the amount of time that a program is allowed to run. So before any process is given the CPU, the process will tell in advance how much time they need to complete. So that time can be used to set as a timer so that when that time is up, the operating system can check on the process to see whether it has completed or not, right? Let's look at process management. We have already said, please, if you have any question at any point in time, you can ask, right? Are you with me?
Yes, sir.
Okay, good. All right, good. So remember, we have said that a program in execution is called a process. A process can create sub-processes. Whilst a process is being executed, if there is the need for the process to create child process, it has the mandate or the power to do so. An example, you are running Microsoft Word document. That is considered one process. Whilst your Microsoft Word is running, it has to perform another process like saving a document. Or you want to do mail merge. This Microsoft Word process can create a child process that will be doing the saving. It can also create another child process that will be doing the mail merge. Okay. Now, a sub-process or the sub-processes that are created by a process can execute concurrently. So whilst you are saving your document, you could be doing mail merge at the same time. The resources that are needed by a process to execute are given before or during the runtime of the process. So when you double click on a Word document, all the resources that are needed are given to the Word document. When you run your Facebook, all the resources that are needed are given to it. Whilst it is executing, if it requires more resources at runtime, those resources can be assigned to the process. So it is not static. We have given this Word document these 3 resources. Whilst it is executing, if it needs additional resources too, we can no longer give it to it. The operating system can still give the needed resources to the process. When we say resources, what are we referring to? We are referring to the CPU time. Remember, we said that after the timer elapses, if the process has not finished executing, we can give it more CPU time. Another resource is the memory. If the process requires more space on the computer memory, the operating system can still give it. If the process needs to access a file, the process can be given that file. Yes, Prince Miller, you've raised your hand.
Yes, sir, please, I have a question. So in the process where, let's say my machine has 2 core processing unit, and then let's say I'm running an Adobe Illustrator, which is already consuming all the 2 cores. And then I happen to open another high demand software that is also requiring more than the almost all the 2 core processing unit that I have. What happens then? Does it shift or does it pause that of the illustrator to focus on the current one that I'm opening? And how does that one happen? Is it all concurrent or something?
Okay, thank you. So if you remember from our previous class, we said that the CPU time is divided into slots. So assuming this is the timeline for the CPU. Now the computer or the CPU is never working on one process all the time. The CPU interleaves. So your 2 processes or your 2 cores that you have in your system, let's put them together. Let's assume they are one, because they will all work in close communication. So this is CPU time 0. This is CPU time 1. This is CPU time 2. This is CPU time 3. So what is happening is that your Adobe Illustrator is giving CPU time 0. Then the next CPU time 1 is given to the new process that you are running. Let's say you are doing Photoshop. So your Illustrator is giving CPU. So at point 0, a CPU will be working on your Illustrator. At time 1, your CPU will be working on the Photoshop. At time 2, the CPU will switch back to the Illustrator. At time 3, the CPU will switch back to the Photoshop. So that is what happens. At every point in time, your CPU is interleaving. So it will not be executing the Illustrator all through. When it finishes, then it will come to the Photoshop, right? If you run another task at time 4, the CPU, let's assume you open Notepad at this session. At time 4, your CPU will switch to Notepad. Then it will go back to Illustrator, Photoshop, Notepad, Illustrator, Photoshop, Notepad. So that is how the CPU will be executing. The timeline, the CPU time will be divided into slots, and the CPU will be working on each of these applications when they get together. Godwin, kindly mute your mic for us. Godwin, yes. Thank you. Please, do you understand now?
Yes, please. Thank you, sir.
You're welcome. Okay. Let me clear the screen. And if there are no questions, let's go on. So these resources we were talking about are the CPU time, the memory, files, and I/O devices. Okay, when we say I/O devices, don't think too much. The simplest example you can find is the keyboard. The keyboard is an input device. Your mouse is also an input device. The output device, consider it as your screen, okay, or your printer, or your camera, the screen. All these are input-output devices. So when a process finishes its execution, it will terminate. Now, on termination, the operating system will recoup or reclaim all the reusable resources that were assigned to the process. So, like I was telling you, the CPU gave the Illustrator time 0, and then it gave the Photoshop time 1 in that order. At time 3, for example, at time 3, if the Illustrator has finished its execution, that time is not a reusable time. The CPU cannot gain or regain the time 0 and time 1. It has been used already. But the subsequent ones, Illustrator will not have a slot. But there are some resources that are reusable, like the memory space that was occupied by the Illustrator. Okay, we can now remove the Illustrator from the main memory and swap in another process that wants or that needs to be executed. If a file was given to the Illustrator, when you close your Illustrator, that file is a reusable resource. it will be stored somewhere on the hard disk. Your keyboard will not be taken away by the illustrator. Your other devices that are reusable will be reclaimed and stored for later use. Mr. Samuel Ofori, you've raised your hand. Okay, thank you. You've lowered your hand. Okay, so a single threaded process has one program counter which points to the next instruction to execute. We'll talk about threads later on, but a thread is a copy or a process in execution. We say that a process can give birth to sub-processes. Okay, these sub-processes can be considered as threads for now. Okay, now when you have a single threaded process, that is a process that has no child process, a process that has no child process, okay, it has only one program counter that points to the next instruction to be executed. Now, a program is a series of instructions, okay? Assuming you write your C++ program, this is line 1, that is line 2, that is line 3, that is line 4, in that order. All these are instructions. Now, when you take the first instruction and the first instruction is being executed, okay, there is a pointer that points to the next instruction. Okay, that means that at the end of the execution of this instruction, the next instruction to be executed is line 2. So you have the pointer pointing to line 2. Then line 2 will also have a pointer that is pointing to line 3 or code 3. Okay, so this is a single threaded process. Now, what happens to a multi-threaded process? In a multi-threaded process, you have sections of the instructions being executed under different threads. So let's come back to our program again. This is line 1, this is line 2, this is line 3, and that is line 4 in the program. These are instructions. Now, in a multi-threaded process, what happens is that perhaps you have two processes. One CPU is executing line 1, another CPU is executing line 2 at the same time. Therefore, the program counter and the next instruction is not easily determined, unlike a single threaded process where only one CPU is executing the instructions. So you know that when the CPU finishes with line 1, it will go to line 2. When it finishes with line 2, it will go to line 3. But on a multi-threaded process, you have different sections of the instructions being executed at different times, and therefore the management becomes different. We will talk more about this when we do threading, multi-threading. For now, let's end here. Okay, the execution of such a single threaded process must be sequential. Like I said, sequential means line 1 finishes, line 2 goes, line 3 goes, line in that order. The CPU executes one instruction of the process after another until the last instruction is completed, which means that the process has completed its execution. Are you with me?
Yes, sir.
Any questions? All right. If there are no questions, let's continue. So the operating system is responsible for the following activities when it comes to process management. Okay, 1, it is the work of the operating system to schedule the processes and the threads on the CPU. So if a process has to be executed, the operating system has to do the scheduling. The operating system is also responsible for creating and deleting both user and system processes. After a process completes its execution, it is the work of the operating system to delete that process from the main memory. Also, if a process is created, it is done by the operating system. Excuse me, please. Hello, sir. Now, the third one also is that the operating system is responsible for suspending and resuming any process. When a process requires an I/O, for example, that process is taken from the main memory, that is the suspension. Then it is given to the I/O control unit. When it finishes with the I/O execution, it has to be brought back into the main memory, that is the resumption. All right, so it is the responsibility of the operating system to perform this suspension and resumption of the process. The operating system also provides mechanisms for process synchronization. Process synchronization, assuming a process gives birth to multiple processes. So this is process A. This process A has given birth to process B. It has also given birth to process C and also process D. It is the work of the operating system to synchronize the execution of all these sub-processes so that at the end, they all achieve the primary goal of process A. Okay, if B is going to use a resource, it must be provided. If C needs a resource, it must be provided. If D needs a resource, it must be provided. They should all do this in consultation or in close communication with their parent process. That is the synchronization. And it is the operating system that provides that. Finally, the operating system provides mechanisms for process communication. I think that has been explained already. These are sub-processes. They are children of the process A. As they execute, they must be communicating among themselves. This is done by the operating system. Again, if there are multiple processes executing at the same time, assuming this is process X, this process X must also be executed in close communication with process A because they are all using the same memory space. They're all using the same CPU. So there must be some communication between the processes. So we say that inter-process communication and intra-process communication. So inter and intra, okay, that is between processes and within the processes. All these communication are taken care of by the operating system. All right, please note this down. It's very important. These are the operations or the activities that the operating system undertakes when it comes to process management. All right. Any questions? If there are no if there are no questions, let's go on. Let's look at memory management. Remember that we have said in our previous class that the main memory is central to the operation of any modern computer system. Why? Because it is from the main memory that the CPU picks its instruction. Okay, the main memory is a repository of quickly accessible data shared by the CPU and other I/O devices. The central processor or the CPU reads or writes instructions from the main memory during the instruction fetch and the data fetch. So these are two cycles, okay, in the execution of a process. We'll come to that. We have the instruction fetch, where the CPU fetches the next instruction. And then we have data fetch, where the CPU also fetches data. We will talk about this later on. Now, on the completion of a program terminates once the processes in a program all execute. The program has finished its execution and it must terminate. When it is terminating, the memory space that it occupied on the computer memory must be declared available. Okay, if your tempo run covered this section of the main memory, when you close your tempo run, it has finished its execution. Therefore, the operating system must announce that this main memory space is available. Then the next program can be loaded into this memory space. Okay, so to improve the utilization of the CPU and the speed of the computer's response time, general purpose computers must keep several programs in the main memory. You want to be able to respond to your user frequently. Therefore, you keep more programs in the main memory so that the CPU can be interleaving them on the timeline as we drew earlier in this class. In memory, this is actually a continuation of the previous one. Okay, so several programs in memory that will create a need for memory management. So because we have several programs on the computer memory at the same time, then we said that there is the need for memory management. The operating system is responsible for the following activities when it comes to memory management. So what does the operating system do in the management of the computer memory? One, it keeps track of which parts of the memory are currently being used and by whom. So who is using this part of the memory and at what point? Number two, the operating system decides which process and data to move in and out of the memory. Number three, the operating system is responsible for memory allocation and deallocation, copying of a program into the main memory and removing of the program from the main memory, assigning memory to a process and taking back the assigned memory from the process. All right, let's look at storage management, the file system management. Okay, so you know what a file is, a collection of related information that is defined by its creator. Files are normally organized into directories to make them easier, what we call folders. Okay, when multiple users have access to files, it may be desirable to control by whom and in what ways files are accessed. You have multiple users accessing the same file, and you must have to find a way to control the access. At every point in time, you should know who created a file, who is using a file, what type of usage. Is it reading? Is it writing? Or is it appending? All these must be known. Okay. The operating system is responsible for the following activities when it comes to file management. Okay. It aids in the creation and deletion of files. So when you create a file, when you create a folder, when you save your document, okay, it is the operating system that actually creates your folder. So at that time, when you right click and you do create new folder, the operating system switches from the user mode into the kernel mode, then it will create the folder. When you click on File, Save, then you get the Save As dialog box. You enter the name of the file, Immediately you click on save. The operating system switches from the user mode to the kernel mode and creates your file or writes your file to the disk. The second one is creating and deleting directories to organize files. So the folders that we create, the folders that we delete, the folders that we copy, the folders that we paste, all that are done by the operating system. Number 3, supporting primitive for manipulating files and directories. All the necessary resources that you need in order to manipulate your file and your folders are being provided by the operating system. Sometimes your Word document is created on Windows XP. Okay, you use your Windows XP to create a file. You bring it to Windows 2010 or Windows 10. You double click on your file created on Windows XP, expecting it to open on Windows 10. It is the operating system that needs to provide all the necessary resources in order for your XP file to open on Windows 10. That is not our business. We don't really care. The operating system does that. Number 4, mapping files onto secondary storage. After you close your Word document, now currently my file, this slide that I am showing you is currently on the main memory. Immediately I close it, it has to be copied from the main memory into the secondary storage, that is the hard disk. Okay, before I double click on it from the hard disk, then it came to the main memory, and now you are watching it. Okay, so it is the operating system that is responsible for these mappings, moving files from and to the secondary storage and the main memory. Finally, number 5, the operating system that is responsible for backing up files on stable, non-volatile storage media. Let me give you a typical example. If you are working on Word document, Microsoft Word document, for example, or let's say PowerPoint, and Evangelist, kindly mute your mic. Thank you. All right. So assuming you are working on Microsoft Word or a PowerPoint document slide, and you don't save it, and your phone or your computer goes off, what happens? If you turn back your computer, sometimes you get your file being restored. The file that you did not save, it will be restored. Though you may have similar slight losses, your file will one way or the other be restored, and you can resume from wherever you were. Okay, that is because the operating system is performing backup. As you type your document, whether you save it or not, the operating system has now been artificially intelligent, and so it will be backing up your file, it will be saving your file small. Another example is if you really want to back up your file, it is the work of the operating system that does it, copying of your files from one location to another. All these are done by the operating system. Are you with me?
Yes, sir.
Any questions?
Okay.
All right. So that is the file system management. Okay. Then we have the mass storage management. Most programs are stored on a disk until we load them into the main memory. If you have your Temple Run on your phone, it is not in the main memory all the time. It is in the hard disk. So if your phone has 128 GB, okay, your Temple Run, if it is 5 GB, it is stored on this 128 GB somewhere safely. Okay, until you run it, it will be here. The proper management of disk storage is of central importance to the computer system, because all these programs are stored on the hard disk or the disk storage. The management of this is very important. If we are not able to manage the disk storage, then the phone will not be efficiently or smoothly used as we have them now. So what does the operating system do in the management of the mass storage? These are the activities. Number one, the operating system manages the free space. That is why at every point in time, you can go into the disk and view or verify how much storage is left unused. If you go to the properties or the settings on your phone, you can always find out how much space is left unused. That is because your Android operating system is at work. The operating system also allocates storage spaces. Like I was saying, the Temple Run. When you install your Temple Run, operating system copies all the file in the Temple Run onto your hard disk or your mass storage. Okay. It also does disk scheduling. Disk scheduling. Remember, we said in our previous class that there is something called the disk pool. Sorry, the job pool that stays on the disk. This is part of the disk scheduling. Okay. When the CPU when the main memory is full and needs to take some virtual memory, this is done on the hard disk. And all these fall under the disk scheduling. The speed of operation of a computer may hinge on the speed of the disk subsystem and the algorithms that manipulate the subsystem. So you know that the speed of your disk subsystem is very important. And that is why when we talked about the SSD, the solid state drives, this SSD technology, we said that they don't go to sleep. There are internal batteries that keep them alive. And so the speed is high. You don't have to spin the hard disk before you read data from them. The hard disks are already, they are all the time ready for access. And hence the speed for this SSD drive. Are you with me?
Yeah.
Okay. Let's go to the next slide then. We have a cache. Let's talk about caching. We said in our previous note that apart from the main memory, the CPU can read data from cache and registers. Okay, so what is a cache? A cache is a temporary storage where information is copied for faster storage while in use. So instead of your CPU copying information to the main memory, sometimes for fast retrieval, the CPU sends the information to the cache. It is a temporary storage, small in size. For example, if you open your browser and you visit www.google.com, then you go to another browser, www.gctu.com. Then your GCTU saves information like the image, the logo. It saves information like the banner on the page. It saves information like the image, some small images. Instead of saving them on the main memory, the CPU will save this in the cache memory so that the next time you load your gctu.com, it will load faster. So you notice that the first time you visited a page on your computer, it was slower than the subsequent visits. That is because some of the information are stored in what we call the cache. That will come in later on. There are internal programmable registers that provide a high-speed cache for main memory. We also have caches that are implemented totally in hardware. For instance, most systems have an instruction cache that holds the instructions expected to be executed next. So if you have a program that is made up of instructions, instruction 1, 2, 3, 4, 5. For fast retrieval, while the CPU is executing instruction 1, the second instruction or the next instruction will be copied into the cache. It is very faster for the CPU to pick information from that cache than it will if it goes to the main memory. So it's all about helping the computer to process data fast. Without this cache, the CPU will have to wait several cycles while an instruction is fetched from the main memory. In the absence of this cache, the CPU will always have to come to the main memory to pick the next instruction. These are however, outside the control of the operating system. This type of cache arrangement is not part of the operating system. It may be part of the application that is being executed. Caches have limited size. Okay, so the cache that we are talking about, they are flash memory. Okay, and they are smaller in size, and therefore management of this cache is very important. Okay, otherwise you run out of caches and the speed of your computer will be compromised. Now, let's go to the protection and security. If a computer system has multiple users, and also if the computer system allows the concurrent execution of multiple processes, then access to these must be regulated. Mr. Abraham, your hand is up.
Yes, please. So I wanted to ask a question about the storage.
Okay. Let's go on.
So please, sometimes when a storage is full, or when you have so many things that makes it full, I think sometimes it crashes.
Yes.
And sometimes when you make a retrieve, maybe when it's 500 gig, it can, when sometimes you make the retrieve and it comes back, it sometimes comes to like maybe 20 gig or like 50 gig. I want to know what causes that.
Okay, so data loss is what you are talking about. When your system crashes, it is a different ball game altogether. The system crash may be due to like you have said, your memory becoming full. Are you referring to the disk space or the main memory space?
The disk space.
The disk space. Okay. So if your disk gets full, it's sometimes or most of the time it does not affect the operation of the CPU, because the CPU does not take data from the disk itself. It takes the data from the main memory. Now, when you close your work and the what do you call it, the process or the program has to be copied back to the hard disk, that is where the problem comes in. So in an attempt to copy or move your file into the hard disk, if there is no space, now what happens is that, the operating system is also residing on the hard disk. So whilst your work is being done in the main, maybe a chunk of the operating system was copied from the main memory into the hard disk. When your computer is overwriting, when it's copying back into the hard disk, it has to overwrite some of the files. And sometimes there will be that contention over power. Maybe the memory location it is trying to overwrite is occupied by a high priority file or something like that. So in the attempt to resolve that conflict, your computer will crash or it will shut down. When you turn it back on, the operating system will reorganize everything. If there is data loss, then there is a serious problem. The data loss has nothing to do with the operating system. Maybe some of your files are corrupt, and when you resume or when you when you restore the files back and you get less than what you had, this is because perhaps some of the files, the memory locations are corrupt, and so you could not retrieve the data from those memory locations. You know, if you remember in our previous class, we said that the hard disk is organized into tracks like this, and the tracks are further divided into sectors, okay, like this. So if in the attempt to, the rivalry over the memory location, okay, if this sector was destroyed, for example, when you retrieve and you get the data from these two sectors, they will definitely be lesser than the total capacity of the hard disk. So when let's say you have your 500 GB and you recover your files and you get 30 GB, it means a chunk of your sectors on the hard drive were destroyed. You understand? Is it okay now?
Yes, please. Thank you.
You're welcome. All right. If there are no questions, let's continue. Okay. So mechanisms in the operating system ensure that the files, the memory segments, the CPU, and other resources can be operated on by only those processes that have gained proper authorization from the operating system. So these computer resources can be accessed only if a process has been properly authorized. That is the protection of the operating system. Operating system ensures that all the computer resources are only accessed by processes that have been properly authorized or authenticated. This protection is the control of access to processes or resources that are defined by the computer system. It is the job of security to defend a system from external and internal attacks. Okay, so protection is the control of access to the resources, and then the job of security is to protect your system from attacks, be them internal or external. These attacks include viruses and worms, DOS, denial of service attacks, identity theft, theft of service, or unauthorized use of a system. The operating system provides all these protection and security. Are you with me? Any questions? All right. We also have distributed systems. What are distributed systems? These are systems that are physically separate. So you have one system in Office 1, another system in Office 2, another system in Office 3. But all these separately, located systems work together as one system. If you have a process, all these systems work together to execute one process. That is what we call distributed system. So you may have 2 or 3 computers put together and they all act as one computer. Okay. These are possibly heterogeneous computer systems that are networked to provide the users with access to various resources that the system maintains. A network is a communication path between two or more systems. Distributed systems rely mainly on networking for their functionality. And you know that TCP/IP, that is the Transmission Control Protocol, stroke IP, is the most common network protocol that is used in this distributed system. Although we have other technologies like the ATM, the asynchronous transfer mode. Some of these are used, but the most common one is the TCP/IP protocol. Okay, and then you know a MAN, Metropolitan Area Network, is an example of a distributed system. Okay, all right. So this will bring us to the end of our first chapter, chapter 1. There are 3 assignments. The first one is on special purpose systems. Research on special purpose systems and document your findings. That's the first assignment. Assignment 2 is on computing environment. Conduct a research on the various computing environments and document your findings. Then lastly, you have open source operating systems. Conduct a research on open source operating systems and document your findings. These are 3 assignments that I want you to do before next week. Lumumba, your hand is up.
Yes, sir. To some of us, due to the how will I say, the information that came earlier.
Okay.
The information that came earlier about the swapping of the classes, we're not able to join the first class as we're talking about.
Yes.
So today happens to be the first class that we are attending with you. So we'll be very glad if you can get us the material.
Okay, thank you. So there is a material on the GCTU online platform. You can go there and download them for your use. Also, I will send the material to your class reps so that they can circulate them on your various platforms for you. There is also a video. As I'm speaking, I am recording